So far, we have seen all the analysis. We are about to complete the course. Still, three modules are remaining. Mm, but the last two modules are very important, week 10 and week 11. Week 12 is just application that you can go through by yourself. We will help you in doing that. That helps in understanding the overall lecture. But until week 11, it has all the analysis you need to really know about it. Right. We are starting week 10 today, module 10, which is state space, based on state space analysis. Actually, this is a very interesting topic out of all we have studied. Transfer function is one age, state space is another age. So we are about to start week 10, which is based on state space analysis. First, we saw some modelings of system. Then we saw some mathematical representation or analysis tools, whatever we call it. There's Laplace, some introduction about Fourier. From Fourier, we went to Laplace. Most of the things we saw Laplace, convolution, initial value, final value theorem. So slowly we started transfer function analysis, where we saw how to represent a system using differential equation, and from differential equation how can we write it back to transfer function representation, and from transfer function or using transfer function representation we did time response analysis, where we saw some of the specifications of the systems like rise times, settling time, overshoot, what else? Peak time. Then comes steady state analysis. Until then, it's only time domain. Then we saw a tool called root locus with one day open loop. How can we analyze the system or how can we make a control system out of it? We also saw PID controller. So until then, it is time domain space based systems. Then we switch to Bode plot, which comes under frequency response analysis. And we saw Nyquist plot. Again, we switch back to time domain, compensated design based on root locus in week 8. Then we switch to compensated design based on Bode, which is again a frequency domain analysis. With these tools we have done. Right, whatever tools we have studied before, we implemented those tools to design a compensator that otherwise called as controller. Now in week 10, it's completely different analysis. Now we are going to do what we are going to do now is state space analysis. From this, we will try to do controller design based on state space representation or something. A very common form to represent all this is it's anywhere we are going to do only the system representation or plant representation or anything in this world. If you want to represent mathematically or in a way to communicate with each other of who shares same interest. It's like a language medium. The state's system representation as a language medium, we have three different representation. Majorly it is, now we are going to focus on transfer function representation, state space representation. Apart from this, a system can be defined using differential equations in continuous time, difference equation in discrete time. This is for continuous, this is for discrete time equations. So these are all different way of representing a same system. A single system can be represented in different forms. Each of the forms has its own advantage and disadvantage. So far we have covered most of the basics, all the analysis we need for transfer function based representation systems. We are going to see the state space representation. Before that, why do we need these two representations? That is the major point of view. So if you want a transfer function representation, in general, how do we define a transfer function? Laplace of output divided by Laplace of input at zero initial conditions. So here, that Laplace of output after the transfer function, it is representation. We call that numerator as zero, denominator as pole. This is denominator. So for stability, what do? We use only the poles. That is the denominator of the transfer function. So far we have done this. Now there is a catch here. It assumes all the transfer functions assumes zero initial conditions. Right. This is one of the catch. The second catch what we used to do is, I don't know whether you think in this point of view. So far we have used only the single input, single output system. For example, if I take a system, I always consider R of S and I consider C of S or something Y of S as output. I have never considered system R1 of S, R2 of S, C1 of S, C2 of S. It is not possible using the transfer function. So when it comes to higher order systems, even higher order systems up to the third order, fifth order, we can use transfer function. Analyzing that stability, we use route Hurwitz array and all. So far, we can manage higher order systems also with transfer function, but never multiple input, multiple output systems. So the first point here to remember is MIMO, multiple input, multiple output systems cannot be represented using a transfer function. So we have to represent, if in case, if you really want to represent the MIMO system using a transfer function, then you have to write a transfer function. For example, for two input, two output system, TDO, two input, two output system, I might write like this. Y1 of S by R1 of S, transfer function 1, Y2 of S by R2 of S, transfer function 2. Will this be enough? Do you think? If I have a system and I have an input R1, input R2, Y1, Y2, whether these two transfer functions are enough? What do you think?
Yes.
Will be enough. Gayatri says it's enough. Anybody has any different opinion? Aditya, Manoj,
No, ma'am,
Sayantan,
I think it's enough.
it's enough. Manoj, Sayantan, enough. Okay. Sayantan, you're ready to reply.
But ma'am, this also assumes that Y1 is in no way affected by R2, right?
Yeah, that's what I was trying to get it. So you might also need to analyze this, right? If I didn't give that assumption. right? This will also be a point of concern here. So you need this much transfer function to represent a simple two input, two output system. Other than single input, single output, it's going to be tedious for any kind of inputs and any kind of outputs. So this is the one drawback of transfer function representation. The next drawback is the system should always be represented under the initial zero initial conditions. So if I have if my home is here and I want to go to my institution somewhere here, so I want to calculate the distance from here to here provided the speed. So with the speed I have to mention from home till the institute. I cannot say at some point of time I have been coming in this speed. With that information, nothing could be inferred out of it, right? So always at every point of time, starting from the initial conditions, it should be done. So physically, it's not feasible. For example, any car or any physical system will start from rest. That's why we always make it simple by assuming it's zero initial conditions. So whenever before you turn off a fan, before you start an engine, it will be in zero initial condition. So it's always life was easy until we use transfer function, assuming all zero initial conditions. So for some systems, there are MIMO systems. Sometimes there will be internal energy stored, which is not equal to zero. If you want to include all the dynamics of the system, assuming zero initial conditions will be approximate the system, but it won't explicitly mentioning the dynamics very clearly. So if you want to implement a higher order control, for example, advanced control, not just PAD or some model predictive control or some advanced control techniques, then you assuming the zero initial conditions will again approximate it. You won't get a exact control input for that. So zero point 0.2 decimal places accuracy you cannot get in that cases. So you need some other broad assumptions where actually the physics of the system starts, or where actually the dynamics of the system relies on. So that kind of analysis can be done using the state space. State space representation doesn't assume anything like zero initial condition. You can start from any initial conditions and yet you can represent the system in this form, state space representation. And it is very easy to represent multi-input, multi-output system using state space because it uses matrix representation, not any denominator or numerator proper transfer function. Nothing it has. So representing that using a matrix representation will be easy for a MIMO system than the transfer function representation. Right. I will just list out the things in words. This is transfer function, SS is state space. So CISO, this is okay for CISO. This is okay for LTI system, easy to represent a single input, single output, easy to represent LTI systems. And this is more feasible to represent MIMO system. SISO can also be done, but doing MIMO also easy here. And this also can be used for LTA and LTV system, linear time invariant and linear time variant systems. And it assumes zero initial conditions. There are no assumptions on the initial conditions here. Right. These are all the overall thing you need to know about this when compared to the transfer function. More intuitive way to tell this is this cannot show internal behavior of the system. This can be used to represent the physical states more clearly. With this introduction, I am moving to state space analysis. State space analysis mainly depend on the thing called state variable. State variable tell you where your current status of any system, whatever system you are considering. For example, if I consider state variable x, if I run, if this is my system, I'm giving one step input from 0th second to 10 seconds, let's take. Okay, some output I'm getting. So from 0th second to 10 second, I am applying some step input. I'm applying some step input, maybe unity step input, and I'm getting some output out of the system. And I can say at this point 5 where my system state variable is, or what is the status or state of my system at that current time being, you consider within the period of time you have given a input. Right. This represents the state variable. State trajectory is, as the name suggests, from the starting point to end point, what was the status of the system? This is the state trajectory. So it at 0 it was 0, at 0.1 it was around zero point 0.2. So this over a period of time, the states propagates like this. So this represents the state trajectory over a period of time the input has applied to the system. Then state transition matrix. So generally, your state space will be represented using these two equations. We have different names for different variables represented here, where x is the state variable that tells where the state is at any particular interval of time you are considering, and y is the output matrix, a is the state transition matrix, B input matrix, C output. C is actually output matrix. So Y represents the output. So in general, what is the output? C represents the matrix corresponding to the output variable explicitly. So
Ma'am, just a quick question.
what?
Just a quick question, ma'am.
Yeah, yeah,
Ma'am, in the above thing, you just wrote that we are going to monitor the internal state of the system now.
yeah, yeah.
So, what does that internal state exactly mean? Because earlier in the transfer functions, we were
Mm-hmm.
just considering the input and the output, right?
Mm-mm-mm-mm. Yeah.
So, what is this internal state exactly?
Okay. So I will give you an example. For example, if I consider a vehicle bicycle model, so if you have a car like this, so which has these two tires, I'm just putting tires outside to see. So what we generally used to do to approximate all the dynamics. Okay. First of all, there are two types of modeling. One is kinematic modeling, another one is dynamic modeling. This kinematic modeling assumes that the states that are not physically related to the system. For example, acceleration, velocity, position. If you replace this car, if you replace a Toyota car with a Tata car, this won't change. For all the cars, whatever speed you are going, this will be constant. But dynamics doesn't work like that. Dynamics will be unique for each and every system. For Toyota car, there will be little dynamics. That for Tata car, the dynamics may vary because they use different kinds of spring constants. Each and every particular small objects they are using in the vehicle contributes to the dynamics. So using these two different dynamics, let's assume we are using these two different dynamics. So this state represents if there is a car, I am just using an acceleration and I'm getting some speed. This acceleration is in terms of accelerator we use, right? In the down, we used to press on the accelerator, right? Whatever acceleration rate you are giving, that much speed will be you will get. For example, you raise from 0 to 100, speed will also go from, for example, 0 to 200. So it is mapped linearly. Whenever you press 5, that will go to 10. So somehow linearly it is related. What this transfer function will do is, transfer function will take the input of 100 accelerometer and take the output of 200 of the speed, and it relates between these two and tells you the dynamics of the system with this only, whether the system is stable or unstable. Only this information. You don't really need any information about the system's internal behavior. Coming to the internal behavior part, when it comes to a state space analysis, state space will tell you how your brake worked. In between, you raise from 0 to 100, that goes to 0 to 200. This will be taken into account. This will also consider friction. So, how well the interaction between your tire and the road was, whether it is slippery or it has very good friction. This kind of relationship also you can get it out of the state space relationship, considering the states you are using for your representation. So this is the main difference between your transfer function and state space representation. Only using input and output, we will be able to tell some of the behavior of the system, like most probably whether the system is stable or not, because I want to ultimately design a controller. If the system is stable, I want to design a controller to get a desired output outcome. In state space, I will do the same thing. I'm going to ultimately design a controller, but I will get more information when compared to transfer function about the system. This is the basic two difference between the transfer function and state space. Any, like, anywhere you missed here? Should I be more clear in any part? Do you understand?
Okay, so as far as I understand it, when we have multiple things like contributing to some output, like in
Mm-hmm.
this case, the accelerator is the main input,
Mm-hmm.
which is converted into speed of the car.
Yeah.
But there are other factors like maybe, like you said, tire friction
Yeah.
or some air resistance or something.
Mm.
So in those cases, we are supposed to use this variable thing.
In those cases, you will get more accurate information about your system so that you can do more accurate control when you design a control.
All right. Okay.
So for mission, whatever, missile launch and all, only transfer function won't be enough. That kind of complicated system requires complicated analysis. You need to know what is the temperature inside the missile, what is the temperature outside the missile. So that kind of calculation you need more sensors and more information. So that time state space will be very useful for you. But if I just do want to do some control in my household, I'm not very fond of accuracy. Just if the work is done, that's okay. With minimal effort, I want. Then I can go with transfer function. No, no problem. But the main thing is, for multiple input, multiple output system, you cannot use transfer function at all, even if you want minimal control.
Okay, ma'am. Got it. Thanks.
Right. So these are all the representation. This is how we represent a system in terms of state space, where individually I will explain what are all each system. Let us take A. A is called as system matrix or state transition matrix. We will use this interchangeably, and this tells the natural dynamics of the system. Most of the information about the natural dynamics of the system lies in this matrix, A matrix, and this is also responsible for stability. We will analyze this matrix if we want to find whether the system is stable or not. So this tells the interconnection between the states, all the information about the states, how the states evolve, because this is a system matrix or a state transition matrix. We can also call this as system matrix. It tells about the system. That's it. Very simple. B matrix is the input matrix, where this tells about the input according to the name. So how inputs affects the states, this will tell us. And if you want to see whether the system is controllable or not, we will study shortly what is controllability and observability and everything. Just for now, I'm just giving an introduction. Look for this. keyword later. Okay. And C is the output matrix. It tells about the output. In depth, we want to know which states of the system can be measured or unmeasured. That can be done using this C matrix, or this helps us in observability. Again, this is again a keyword that we are going to study in later concepts. If you want to study this, we want to first know what the state space is. That's what we are doing right now. Then D is the feed forward or feed through matrix. This is the one that tells direct input output relationship, as in transit function. We usually do make it zero because it won't be much useful for us. So if you want to represent any system, just use this equation to represent the system dynamics using the state space representation, where A belongs to e power, sorry, r power n cross n. R power, we call this as a real space, where it is of real numbers of different dimensions, where n represents the dimension of the system. N cross n means it's the nth row and nth column dimension. For example, 2 cross 2 means it's a A11, A12, A21, A22. This is 2 cross 2. Similarly, we have n cross n. This is the n cross n. So A generally depends on n cross n, where n is based on the system you are assuming. Similarly, B belongs to R power n cross m, C belongs to R power P cross N, D belongs to R power P cross M. So you know the associativity, commutative property of all the matrices, right? Distribution, association, commutation. So based on that, if you put this, for example, A belongs to R power N cross N, where your Xn will be R power N. Yn will be R power M, I guess. That I will clarify. So if this is R power N cross N into R power N plus B is R power N cross M, U is R power M, right? Y will be R power 3 cross N, R power N plus R power P cross M. This is R power M. So that's how your state space representation would be. Okay, right. Now we will do some problems, like I will tell how to um, write a state space representation for any system. Before that, I want to revisit the topics we did from transfer function. So going from transfer function to state space, I guess it will be easy. What do we generally do? If I give y double dot plus 6y dot plus 5y is equal to some 5x, let's take. So I want to represent I'm asking you to find the transfer function for the system. What do you usually do? Since we are going to find the transfer function, we will assume all the initial conditions are zero unless it was given. Right. So y dot of 0 is also 0, y of 0 is also 0. Substituting, expanding this using Laplace transform, what we will do? S square y of s minus s into y of 0 minus y dot of 0 plus 6 into s y of s minus y of 0 plus 5 into y of s equal to 5 into x of s. Any doubt in this line? You are familiar with this, right? This is a Laplace of differential equation, dy
Yes,
by dx. Yeah. So now if I write s square, all the initial conditions are 0. So this will be s square plus y of s, 6s into y of s plus 5y of s equal to 5 into x of s. What is transfer function? Laplace of output by Laplace of input. So y of s by x of s, I'm rearranging everything. 5 by s square plus 6s plus 5. So we have this transfer function. This is our overall transfer function representation. If I want to find the stability, what will I do? I will just take the characteristic equation. Denominator will be equated to 0. Then I will find the factors of this that we call it as poles. Denominators, factorization of denominators will be the poles. So this will give me s plus 2 into s plus 3. That will work. So s is equal to minus 2 minus 3. So poles lies in the left half of the s plane. So the system is stable. That's how we define the system. Right. There is a little bit change from here. We are going to do the same thing. This is also a proper approach to find the transfer function. Instead of doing this, what if I say I am introducing a concept called converting nth order differential equation to n first order differential equation. For example, if you have y power n plus a n minus 1 y power n minus 1 plus a n minus 2 y power n minus 2 until plus a1 y dot plus a naught y equal to u of t. So here what we got, a y power 2 or double dot, I will say, instead of y square. This is y double dot plus 5 y dot plus 6y equal to 5x of t. So if I compare these two, this is y u of t, 5x of t is equal to u of t, where a naught y is here, a1 y dot is here, some another term after this will come from a power, sorry, some coefficient into y double dot. So I can say a naught equal to 6 here, a1 equal to 5, some a2 equal to 1. So these are all the coefficients of y, y dot, y double dot. Now I want to represent this nth order equation. This is a second order or third order? Which order equation?
Second.
Second order. So I want to change this second order equation into two first order equation. That is the format of nth order equation to n first order equation. Two represented in terms of a state space equation. How can we do that? First, we need to assume whatever variable they have given, y, c, b, whatever variable they have given, just assume x1 equal to y, the least variable. Assign that to x1. Now, if I differentiate both sides, what I will get? X1 dot is equal to y dot. I call this as x2. If I again differentiate this, x1 double dot equal to y double dot, I call this as x3. Can also be defined as x2 dot. Any doubt in this? Just please process this slowly. Understand what I'm trying to do. Then ask me question if you don't understand. I have a variable y here. I have a variable y here. I am assigning this y to some variable called x1. I'm just differentiating both sides. Then x1 dot equal to y1 y dot. That I am assigning a different variable called x2. Now again I am differentiating that one more time. That is x1 double dot equal to y dot. I am giving another name called x3, but this time I'm not going to use this, but I'm going to represent this in terms of a differentiator. Any doubt in this?
No, ma'am.
Right.
No, ma'am.
Right. From this relation, I am going to write x1 dot equal to x2 from this line. X2 dot equal to some I have to get it. Right. For now, this is okay. X1 dot equal to x2. You understood that, right?
Yes, ma'am.
Yes, ma'am.
Now x2 dot equal to y double dot. X2 dot equal to y double dot. This is what we are going to write. What is y double dot? What
X1
is,
double dot.
yeah, x1 double dot. Instead, can we take it from this equation? We know y double dot, where the equation is y double dot plus 5y dot plus 6 equal to 5x, right? From this, if I equate this and keeping everything this side and I'm putting it here, can I get the y double dot now? I will just substitute it here. Now I will write it as x1 dot equal to x2, x2 dot equal to 5x minus 5y dot plus 6, where I'm going to replace all the y's with the x. Y dot is x1 dot again. So 5x minus 5x1 dot plus 6, right? This is my state space representation. That's it. Is it confusing?
No, ma'am. Understood.
Right. Just replace this with x2 because x1 dot is equal to x2, right? The point here is I want to get all the state variables in terms of dot in the left hand side and some A matrix, and in terms of single equation, not any differentiator, plus B into U1, U2. This is how I want to split. That's why I am doing all these things. Let me do it again once clearly if you have some doubt. Okay, just I'm going to keep 0 for now because that input and all will be very complex for now. We will also solve problems with input. What I'm going to do, I'm going to assign y to x1, x1 dot equal to y dot equal to x2, and x2 dot equal to y double dot equal to whatever equation I'm getting. So this is my format. Now I know x1 dot. This left hand side I know, x2 dot I know. Because this is a second order equation, so I will also get 2 cross 2 matrix. Sorry, 2 cross 1 matrix in the left hand side. If this is a third order equation, I would need another state also to represent. For now, it's a second order, so only 2 states we will take. Now, I am going to write x1 dot equal to x2 as it is. For all the systems you are converting from nth order equation to n first order equation, the first state would be x2 only. You will get the same for everything. Then for y double dot, I am going to keep y double dot in the left side and going to push rest of the things to right hand side, y dot plus 6. So the next equation would be 5y dot plus 6. This is the state matrix. Just to replace everything in terms of x, I am going to write 5y dot. Instead of y dot, I am going to write x2. That's it. 5x2 plus 6. Now I got everything in terms of x dot equal to ax format. Now if I split this, what I will get? First is also x2, second is also x2. So the x1 will be 0, x2 will be 1 minus 5. How can we represent? Okay, wait. 0, 1, 0 minus 5, x1, x2 plus 0, 6, u. Right? If I again do this, 0 into x1 plus x2, 0 into x1 minus 5x2. This equation has come, right? Plus 6 into u. This 6 is a constant. It will be multiplied using u. Clear?
Yes, ma'am.
Right. If anyone have any doubt here, uh, I know initially it will be little confusing. If you start to solve two, three problems, then only it will be clear.
Yes, ma'am.
Okay, we'll solve problems. Then, if you struggle in there, also we will see. We'll try to address those. Okay. For now, this is the concept I want you to learn. You should know what is state space, what each A, B, C, D represents, X, Y, what is it, and how we can represent the entire system from the transfer function. That's so now you don't need transfer function. From the differential equation itself, you can represent the system in terms of state space. This is one point. There is another point. If I give you a transfer function, how do you convert that to a state space equation? That's relatively simple than this because your transfer function is g of s, some numerator by denominator, it will be represented, right? Now, okay, it's a transfer function from state space. Mm, if I just give a transfer function, okay, this is actually a introduction to the next lecture, but okay, let me try this. 1 by s square plus 5s plus 6. If this is a transfer function, then you will, what you usually do to convert this to time domain, you will do partial fraction. So this will be s plus 2 into s plus 3. You will get, so then again we will split this to a by s plus 2, b by s plus 3, then a into s plus 3 plus b into s plus 2 equal to some 1. Putting s is equal to minus 3, what I will get? Minus b equal to minus 1. S equal to minus 2 means a equal to 1. Then I will get 1 by s plus 2 plus, sorry, minus 1 by s plus 3. So this is ready for the time domain representation, right? This is my output. Y of s will be in terms of some input I considered. Good. From this, we want to convert this to a state space representation. Again, we will use this one moment.
अरे मैं ये पूछ रही थी तुम लोग जा रहे थे क्या
Yeah.
जाने का
Okay.
सोचे थे yes ma'am it's clear
Yeah, it's clear. It will be little. It will be like this. So if I give a state space like this, sorry, transfer function like this. So what I will do from here is this is to find in terms of a time domain representation. Now, if I want to do it in terms of a state space representation, then I will just multiply this over this a square plus 5s plus 6 equal to x of s. Then I will do a square y of s plus, it's again normally, since it is a transfer function, zero initial condition itself, right? X of s. Then I will do the same thing what we did for the differential equation. So from this, how I will get y double dot plus 5 into y dot plus 6 y equal to x. So now I will convert this to nth order differential equation to n single order differential equation by assigning y equal to x1, x1 dot equal to x2, x2 dot equal to minus 5y dot plus 6y plus x. That's how I used to do for find it in terms of a state space. Now from state space to transfer function, if I give a state space, but I want to convert it in terms of transfer function. Since we learned this, we will also see this. It's a straightforward idea where you have y of s plus e of s, but I have given you x dot given is x dot equal to a into x plus bu y equal to cx plus du. So I want to convert from this to this. That equation, it's very simple, straightforward. That is g of s equal to c into si minus a the whole inverse plus b. So if I give you x dot equal to 1 0 0 1 x plus 0 1 u, y equal to 0 1 x plus 0 into u. Now I will just substitute. This is A matrix, this is B matrix, C and D. So if I want to substitute this in this equation, what will I get? 0 1, this is C matrix into Si minus A matrix, 1 0 0 1. The whole inverse plus B is 1 0. So this will give me 0 1 Si minus 1 0 0 Si minus 1 the whole inverse plus 0 1 0 1. Inverse means you will first find the determinant. Determinant is Si minus 1 the whole square into, you will swap things, Si minus 1 and Si minus 1. This will be minus 0 minus 0. Nothing changes much, just 0 it is. So this will give me 0 1 into 1 by Si minus 1 the whole square. This will be 1 by Si minus 1. If I multiply this inside, 0 1 by Si minus 1, because the numerator will get cancelled, Si minus 1 Si minus 1. Then this will be 0 into this column, 1 into this element. So it will give me 0. This is a 1 cross 2 matrix. This is 2 cross 2 matrix. The output will be 1 cross 2 matrix, right? So it is 0 0. That is also 0 into 1. It will be 1 by Si minus 1. 0 1 plus B. It's correct only, right? 1 cross 2, it's 2 cross 2, 0 into this 1. 1 is 0, correct. One cross 2. But how this multiplication will be done there? Oh, sorry. This is not plus. Sorry, I made a blender here. It's not plus, it's into. Everything is into. So that's why I'm not getting answer here. Okay. Plus D. So I written that as plus B. Okay. C Si minus A inverse into B plus D. So there won't be any minus here. So everything will be done. It's correct. Now, if I multiply this with this, I will get, this is a 1 cross 2, this is 2 cross 1, then I will get a 1 cross 1 matrix, right? 0 and 1 by Si minus 1. It's the transfer function. So this is the whole transfer function I will get in terms of G of S. So this is from state space to transfer function. Now, collecting all the points, we know from differential equation to state space, we will use nth order differential equation to n first order differential equation. from transfer function to state space, we will first cross multiply and get it in terms of that mm, like Laplace of differentiation. Then we will apply the same nth order differential equation to n single first order differential equation. From state space to transfer function, we will use this formula g of s is equal to c into si minus a the whole inverse b plus d. D is almost zero most of the time, so it will be just c into si minus a the whole inverse into b. That is the maximum value you get. You want something? Yeah. You have any meeting now? Okay, right. I will leave you. No problem. This office is at next to ITM Global. Last office. Did we message you? Let me know if you need this room, okay? Okay, I'm sorry if there's an interruption. Right. The next thing what we left. System model. Okay, we can take this example of system modeling we did for transfer function. Then we will do the same as a practice now. Okay, mx double dot bx plus. No, it's a classic system we used to take. That is m, and I have something like this, and I have a spring. Some. Let me use the same. It's bkmxf, right? P K M. Right. So force is in terms of this. So acceleration will be in terms of this, and speed constant, spring constant will be in terms of this, and your damper will be in terms of x dot. So when we want to write this free body diagram, how will you write mx double dot plus bx dot plus kx equal to f? So this all will be in this direction if the force is in this direction. It's a opposite to that force, collection of all the forces that act at each element that is acting opposite to the input force. So the equation, differential equation will look like this. From this, how will you write transfer function? It will be again s square m x of s with zero initial condition, s b x of s plus k x of s equal to f of s. Then this will be x of s divided by f of s. Then it is 1 by ms square plus bs plus k. Now this is your transfer function representation of the same system. Now we are going to skip this part and do the state space straight away. Mx double dot plus bx dot plus kx equal to f. For now I am going to assume f is equal to 0. So x double dot plus x dot plus kx equal to 0. With f also we will see now. Okay. Right. For now, first what we will do, we will convert this to equation. So x1 equal to x2, x1 dot equal to, sorry. x1 is equal to x. Your variable here is x, right? So x1 dot is equal to x dot, which is also equal to x2. x2 dot is equal to x double dot. Now, what is x double dot? Mx double dot plus bx dot plus kx equal to f or equal to 0. This equation straight. Keeping x double dot here, I am going to write everything else in the right hand side. equal to minus bx dot minus kx x double dot alone equal to minus b by m x dot minus k by m x, because I'm throwing m to the right hand side. Excuse me. Now I can replace this equation to the x dot. Now x1 dot equal to x2, x2 dot equal to minus b by m x dot minus k by m x. Now I want to replace this dot everything with x1, right? What is x1 x dot? X dot is again x2. So x2 minus k by m, x is x1. So it is x1. Now the overall equation will look like this. 0 into x1 plus x2, x2 dot equal to minus k by m x1 minus b by m x2. Just I will give you some second to go through this. I will slowly scroll. We see from the system how did we first write the differential equation, then how did we convert it from nth order to n first order, then how we write the state space. So starting from this differential equation, just go through this. I'll give you a minute. I might do some minus plus mistakes. If you find something, let me. Is it okay? Anybody has any different opinion?
No, ma'am.
Right. So if you understood, please give a thumbs up. I should know how you are getting it. Okay.
Yes, ma'am. Yes, ma'am.
Right. Okay. Good. No. So now we can represent this. We can represent this into a state space. x1 dot x2 dot in a matrix equal to 0, 1 minus k by m minus b by m x1 x2. Plus there is nothing here, so the U matrix is 0. Now I'm not going to consider F equal to 0. Instead, I'm just going to take F as it is. Then how the matrix is changing, that's we are going to see. Same thing, x is equal x1 equal to x, x2 equal to x1 dot equal to x dot, x2 dot equal to x1 double dot equal to x double dot. Now mx double dot equal to minus bx dot minus kx plus f as it is. X double dot equal to minus b by m minus x dot minus k by m x plus f by m. X dot is x2 minus b by m x2 minus k by m x1 plus f by m nothing. Now the equation is x1 dot equal to x2, x2 dot equal to minus b by m or minus k by m first, minus k by m x1 minus b by m x2 plus f by m. Now if I write it as a matrix format, x1 dot x2 equal to 0, 1, 1 minus k by m minus b by m x1 x2 plus, this is in the second equation, right? So first will be 0, second will be f by m into u. Only one input we consider. So it is u. Otherwise, if it is two input, it will be y1, y2. Sorry, u1, u2. So when compared to this equation, B matrix changed, right? If you consider input is 0, B matrix will be 0. If you consider input, B matrix will have some non-zero entering. I hope this is clear. If you have any doubt, please pause me in between. What else we need to
No,
see?
ma'am.
Right. Um, State space representation we did. This is an example you can go through. Cruise control is another example. Like we did for, you can also take simple pendulum and try to write. DC motor equation is another example. I will come to MATLAB part later. We can do some problems in MATLAB also. First, let me do all the concepts today. So this we saw nth order to n single order differential equations we have seen. Transfer function to state space we have seen. State space to transfer function done using this formula. Eigenvalues we have to see, right? Right. We will see what are eigenvalues and how it is related to your system. Now we know this representation ax dot equal to ax plus bx. Consider u equal to 0 now. So how this will be x dot equal to ax. This is the equation. So if I want to find the solution for this equation, how will you tell the solution? Just I'm saying find the solution for this equation. That's it, nothing else. How will you find it in terms of a time domain? Any idea? How do you usually find? This is in terms of
We
exponential.
take x1, x2, it's like that.
We take a Laplace of this, then what you will get? This is d by, sorry, instead of writing this, I can straight away write this. You are familiar with this, right? S into x of s minus 0 equal to a into
Yes,
x
ma'am.
of s double, right? Then this will be s into s minus a into x of s equal to some zero, no input it is. So if you want to represent in terms of input by output by input, then it will be some x of s equal to 1 by s minus a, right? This is going to be my transfer function, not assuming there is some initial condition, but it is not zero, but negligible to zero. Maybe it's similar to zero, but not zero if I consider. Then there will be some initial condition into this. I'm considering. So if I want to convert this in terms of time domain again, x of t is equal to e power at into x of 0. So this is the solution for this equation in terms of time domain, right? So whether this is a stable or unstable.
Ma'am, unstable.
Unstable. X of t, this is t, it's unstable because it is e power at, not e power t. Right. Now, with this, we can say whether the system is stable or unstable or anything. This is one way. So, if I have another equation, let's take ax plus b, not okay. 1 minute, let me charge my laptop. Similarly, if my u is not equal to 0, it will be bu. If I take as it is, then the similar equation or the solution for this will be for the first term ax, it will be e power x naught. If you do the same thing for this, you will have something like this. It won't be negative here. You will have something like this 1 minus e power at b by a into u. So this will be the solution for this equation. Here, if I consider y equal to 0, this term will go to 0. So we will have only e power at x of 0. This can be written in terms of 1 plus at plus at whole square by 2 factorial. It's a expanding, I'm expanding this term using Taylor series. You will get something like this. And all else are the higher order terms. We won't be seeing all those things. So e power at can be expanded using this equation, considering x not equal to 0 for now. 1 plus at plus at the whole square divided by 2 factorial plus everything else I am going to consider as a higher order terms. Keep this in mind. Now, I can say whether your system is stable or not from this equation, right? E power at. So, if this is e power at, it is unstable. If we get something like e power minus at, then it is stable. Then, how really you are finding it in state spaces? E power at is equal to 1 by s minus a. E power minus at will be equivalent to 1 by s plus c. Then this is in terms of here a, this is in terms of here. So this is LHS, this is RHS. So this system would be unstable in general. This system would be stable in general. This is from time domain representation. How can we do the same thing using the state space representation? Only the state space representation. I don't want to find the time domain representation. For example, if I have a system a equal to 0, 1, minus 2, minus 3, right? So my representation is x dot equal to 0, 1, minus 2, minus 3, x1, x2, and maybe x1 dot, x1, x2 dot plus 0, 0 into u. There is no input. I'm not going to consider anything for the input. You have heard of eigenvalues, eigenvectors anywhere in some other subjects, math preliminaries or anything?
Yes, ma'am.
We are going to use the same concept here because the solution to the equation, that's why we wrote this x dot equal to as, which is in terms of state space. The solution to this is e power at, where a represents the system matrix here. So when the a is positive, then it is unstable. When the A is negative, minus A, then the system would be stable. So the stability actually relies on the system matrix A. So based on the nature of the system matrix A, the stability is being determined, right? Where the poles are in transfer function or how the exponential term looks like based on this time domain representation. The same system matrix, how can we get from this A? This is also a system matrix in state space representation, right? So from this, how can we relate this as eigenvalues? The common thing between this state matrix and your solution to the representation x dot equal to a, that is also a state space representation. It's the eigenvalue. So if you find the eigenvalue of a, then you can determine the stability of the system. If the eigenvalue of a is less than 0, then the system is stable. As you saw the same thing in left hand side. If the eigenvalues of a is greater than 0, system is unstable. As you saw, it's in the right half of the system. So for this example, a equal to 0, 1, minus 2, minus 3, we are going to find the eigenvalue, I of a. How do you find the I of a? Lambda I minus a, determinant of this equal to 0. So first I want to do lambda minus a. The matrix will be lambda minus 1, 2. Okay, I will write in steps for you for the first time. Lambda is 0, lambda into I, right? 0 lambda into I, minus a, 0, 1, minus 2, minus 3. Then this will be lambda into 0, 0 into lambda, minus 0, 1, minus 2, minus 3. So this will give me lambda minus 0, 0 minus 1, 0 plus 2, lambda plus 3. So it will be lambda minus 1, 2, lambda plus 3. Now we are going to find the determinant lambda I minus a. Determinant of lambda I minus a equal to determinant of this matrix. How to find the determinant? Lambda into lambda plus 3 minus of minus 2. Lambda square plus 3 lambda plus 2. Oh, okay. This problem
Ma'am, what
happens.
happened?
Actually, this problem happened some 3 times before it happened. All of
Okay,
that
ma'am.
everything is gone.
But the last question only, it's gone, I guess. Oh no, this question we have done. How much question we missed?
Mostly last 20-30 minutes we missed. Okay, it will be there in the live session. I'm been recording only
Huh,
this note.
yeah, that would be good.
Okay.
Or we can just start with a new question, I guess.
Yeah. Okay. The A is again 0, 1, minus 2, minus 3. It will be lambda minus I. So I have made the steps. I'm just going to write it again here in short
Oh,
form.
yeah. Yes, ma'am.
So see from the over or watching the online recording, you can see from the previous step,
Huh.
timestamp. From here, lambda I minus a, it will be lambda into lambda plus 3 minus plus 2. Minus of minus 2, it's plus 2 I'm writing. Lambda square plus 3 lambda plus 2. So I'm going to equate this to 0 to find the eigenvalues. So lambda square plus 3 lambda plus 2 equal to 0. Okay, then lambda equal to minus 1 minus 2, you will get. So both are in the left half of the S plane stable. So in state space, if you want to find the stability of the system, eigenvalue of system matrix, if it is less than 0 stable, greater than 0 unstable. If it is equal to 0, it's marginally stable. Intuitively, why we are looking for the eigenvalue is because our state space representation is also in terms of this. Solution to this state space depends on the e power at, where A is the determinant matrix. A determine whether here the system is stable or not. When A is overall positive, then it is unstable. When the A is overall negative, then it is stable. So the whether the A is positive or negative, that we are finding using the eigenvalues. So this tells the system's properties, system matrix property. That's why we are finding eigenvalue. Now with the eigenvalue for the state
Yes,
space
ma'am.
system, if it is less than LHS stable. Keep this in mind. The other way around, it is unstable. That's it. Okay. Right. Now most of the things are done. I want to represent the solution to this one. Yeah. We will. I have most I'm done with the lecture 1. Differential equation, everything is done. Now we can go to lecture 2. In lecture 2, we have stability. Okay. Okay. This is what we have seen so far, right? So I have written this in the notes before. So how to find the solution to this equation? X dot is equal to ax plus b, where b is not equal to 0 here. So keeping everything here, only for the solution we have seen e power at x naught. That's what we have completed right now. And for e power at, if you want to expand this e power at, it will look like this. E power at is equal to 1 plus at plus a square by t, a square t square by 2 factorial plus a cube t cube by 3 factorial, etc. It will expand until the higher order terms. We will mostly limit ourselves until the second order terms. So now, if you want to find the solution to any system, you have to find the A matrix, then you have to find this exponential terms, then again you will find the solution to this matrix. Instead of doing or going through all these things, instead of going, so for example, in this example, it was given -2, 0, 1, -1. So this is the example. Consider this. I want you to find the solution to this equation. It is in terms of e power ax, where a is given as -2, 0, 1, -1. I'm asking you to find what is x of t. So how will you find? You will consider the solution of equation as e power at. So substituting the A matrix instead of e power at here, it will be e power -2, 0, 1, -1 into t. Instead of calculating like this, I am expanding it using the Taylor series. Then this will become 1 plus at. A is -2, 0, 1, -1 into t plus a square t square -201 -1 square into t square. Up to this, I will calculate. So for this, I need to calculate 1 plus -20 1 -1 into what t it is. T, I am going to keep it as it is. So square of this, how will you calculate a square of a matrix? You will multiply it again, or you will
Yes,
reduce
ma'am.
it to echelon form and do, but we don't have that much time now. So I'm going to use as it. This is the square. I'm going to write as it is
Yes, ma'am.
into t square. So this, if you find all this, 1 is actually not 1. It's an identity matrix. Plus -2, 0, 1, -1 into t plus 4, 0, -3, 1 into t square. This will give me 1 -2t plus 4t square, 0 plus 0 plus 0, 0 plus 1t -3t square, 1 1t plus 1t square. So this is the matrix. So after this, 1 2t plus 4t square, 0, 1t or t plus 3t square -1t plus 1t square. So this is the expansion we have got so far. Now, if you again, how you e power at, you have expanded it to 1 plus at plus a square t square, right? Now we are going to take it back to this. So this expansion, this is e power, means this is 1 plus a is 2 here plus t plus 4 t square, right? Again, this can be written as 2t square. Then it will be e power minus 2t. Similarly, we will shrink back everything. That will give me e power minus 2t, 0, e power minus t, minus e power minus 2t, e power minus t. So this is the overall solution for my differential equation. This is okay if it is a second order equation. You will find. If it is a 3 cross 3 matrix, then it's a headache, right? Doing all the steps to find the solution for this matrix. It's a headache. So we are looking for can any simplest way to do this, any other better way to handle this problem instead of doing all this t's and twos and everything. The straightaway answer is using the Laplace transform again, as we did for the transfer function. Instead of going through all these things, first you will find the S minus Si minus A, the whole inverse for the A matrix, instead of finding it for e power at, this expansion. Instead of substituting on this, we will find Si minus A the whole square. Then from this, we will do partial fraction if needed. Otherwise, we don't have to do. Then just convert it from the S domain to time domain, T domain. As we have done this in transfer function also, right? If you remember, if you want differential equations would be given. So if you want to convert it into the transfer function, first we will apply Laplace transform, then we will do partial fraction and take inverse to find the time domain representation. The same thing we are going to do here to find the solution. So for the same example, now we will solve here. A equal to -2, 0, it's -1 or -2, 0, 1, -1. One minus one. What we are going to do is Si minus A, the whole inverse we are going to find is 0, 0, S minus -2, 0, 1, -1. So it will be S plus 2, 0, -1, S plus Si minus A. This is just Si minus A. For Si minus A, the whole inverse will be, first we have to find the determinant. Determinant is 1 by determinant it is, right? Because this will be adjacent of Si minus A divided by determinant of Si minus A. So Si minus A determinant is S plus 2 into S plus 1 minus of -1, it is +1. S square plus 3S plus 2 plus 1 plus S square plus 3S plus 3. Sorry, it is 0, right? 3S plus 2 it will be. Otherwise, I can keep whatever is, either it is S plus 1 or S plus 2 if it is easy to cancel. Otherwise, S squared plus 3S plus 2. Let's see how it comes. Now, if I want to represent it in home terms of inverse, it will be adjacent. If you want to find, we will replace this values S plus 1 into S plus 2 and we will put minus of this, right? That's what we used to do. S plus 1, S plus 2, 0, 1 divided by S plus 1 into S plus 2. Then this will give me 1 by S plus 1 into S plus 2. Just to see, visualize this. This, if I multiply everything inside, this will be 1 by S plus 2, 0, 1 by S plus 1 into S plus 2, 1 by S plus 1, right? The same we are getting. We are right one. Okay. Good. Now we have this, just since it has to function in cascade, we are going to find the partial fraction for this. Otherwise, we can go ahead. It will be A by S plus 1 plus B by S plus 2. A into S plus 2 plus B into S plus 1 equal to 1. If I put S is equal to -1, A equal to 1, S is equal to -2, B equal to -1, then this will be 1 by s plus 2, 0, 1 by s plus 1 minus 1 by s plus 2, 1 by s plus 1. Right. This is the overall solution for this. Still it is xs. If I want to convert this into xt, e power minus 2t, 0, e power minus t minus e power minus 2t, e power minus t. Now we got the same answer as we did using the exponential Taylor series, right?
Yes, ma'am.
Yeah, what we got here, e power minus 2t, 0, e power minus t, e power minus 2t, e power minus t. The same thing we also got.
तो ऐसे हम लोग
Any doubt?
No, ma'am.
Right. So instead of finding phi of
अरे
t
नहीं
or
बहुत
x of t solution for this,
नहीं
if,
जाऊंगा लेना ऐसा रिजॉर्ट में तो सब थोड़ा एंजॉय करके प्लीज
can you please mute? Yeah. So instead of finding using a, instead of finding x of t using e power at equal to 1 plus at plus a square t square plus etc., we are going to use the steps. One is first we need to find the si minus a inverse. In you while finding this, if required, we will use using the Laplace transform. Okay, while required, if you need, you do partial fraction to find it without a cascade operation. Then you will convert from S domain to time domain by using inverse Laplace transform. This will save us much time when compared to the above this technique. This is technique 1 and this is technique 2. We will go with technique 2. Okay. The last thing I want to explain is what? Suresh sir, next row. Okay, then I don't know. Okay. Now, the last thing I want to cover is the linearization part, which is another important part in this series. How do we linearize a system from a nonlinear point of view? Okay. Before going to this, I want to introduce two things. Okay. Equilibria I have to cover. Linearization and analysis of equilibrium point using some examples. Okay, done. The next concept is linearization of systems. This is in module 3. Okay. Before going into this, we have seen LTI system. Most of the system examples we have seen as a linear time invariant system. We never really touched linear time variant system because the analysis is little complex. It goes beyond the scope of this course. But most we limit us to linear time invariant system. The hard part here is linear. So always the system we took are linear. We never analyze any system that is non-linear. For example, x square, x cube, sin x. We have never came across any system like this, right? Sin x, cos x, any trigonometrical equations or exponential equations. Exponential we have seen, but we use that only to find the stability, not really solving problems based on the exponential system. For example, x dot equal to, I never give any system like x1 and x cube solve this. Find the x1, x2. We haven't done anything like that. It's because All this analysis so far we have done, it works best for the linear system. I won't say it is not for a non-linear system. Non-linear systems also can be approximated into linear and use the same tools. So the idea behind this is, inherently all the systems that are available in physics, physical systems, whatever you see outside, fan, starting from fan, car, everything is non-linear. It was never linear, but we call everything linear because we do approximation of non-linear to a linear. So that's how the world revolves. So instead of finding many difficult things for nonlinear systems which behaves in unique way, in very different way, if you want to start to solve nonlinear system as nonlinear itself, we need to find techniques for each and every systems, and it will be very clumsy and very difficult. What we used to do is, first simply we will consider the nonlinear linearity of the system and approximate system around the equilibrium point to consider that as a linear system. We are just I hope my screen is visible.
Yes, ma'am.
We are approximating the nonlinear system to a linear system and apply all the tools we have studied so far for this linear kind of nonlinear system. That's what we used to do. And there are studies, if you go for higher studies, if you take degrees and another studies, there are really studies going on for nonlinear system as it is. Instead of linearizing those things, how can we keep the nonlinear system as nonlinear itself and do that kind of analysis also there. But most of the time, we will simplify that by approximating the nonlinear into a linear and apply all the tools we have studied so far for a linear system to identify the characteristics of that. Right. How can we non approximate this? This is the whole point of this module 3 of this lecture 3 of this module. So, if I take a nonlinear system, let's take this is a bowl. Consider this as a bowl, and I'm putting a coin here, some or any piece, some round piece I'm putting. What it will do, if I drop it from here, it will go here, 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 here. Again, at some point, it will come to this point, right? Ultimately, we know it is going to settle here. In mathematical point of view, what do we call this as a minima, right? So it is the minimum value of the function that can go. That's how the piece is also going to travel. If I drop it from here, it will go here and there until it reaches this point. So this point is the state where it rests after motion. So this we call it as equilibrium. So once the piece reaches this point, we call the system is at its equilibrium point. So the state won't change until you move. Newton's first law. Once it reaches the equilibrium, until there is some other disturbance or external force acting upon those state, it won't move. It is a comfortable place. For this state, for this bowl, the state is the P I have considered, and the trajectory of the P goes from here to here, here, and until it reaches this point, where is the which is the minima of the system, and this we call it as a equilibrium point, where it is going to stay for the rest of the time until we make some changes to the system, until I disturb the system or until I put my hand and take the P out of the system. So this kind of disturbances you would expect. Until then, it will be in that state that we call going to call it as equilibrium. So now what we are going to do, this approximation I told, right, non-linear to linear, this approximation will always be done in this equilibrium point. Why so? because we are sure that at this point the system won't have any internal changes, right? Until there is any external disturbance or any input force happens, the system itself won't change. I know about it. So based on that criteria, I know the system will be stable, or I cannot say stable. The system will be at rest at this point. So whatever changes I am making, that is the only changes it will go through. There won't be any internal changes that I have to worry about. So we will always approximate the system, non-linear system, into a linear system at its equilibrium point. Any doubt in this? Why, how, what? Any doubt in this?
No, ma'am.
Right. Now, for to find the equilibrium point for any system, that's the next question we have in our mind, right? So now I will take some example from this. Okay, I will take this x1 dot equal to x2, x2 dot equal to minus x2 minus sin x1. x1 dot equal to x2, x2 dot equal to minus x2 minus sin x1. Okay. This is a dynamic equation, differential equation, sorry, state space representation of a simple pendulum. Now we have find non-linearity here. So far we have seen only x1, x2 or a x1, b x2. Nothing like sign. Now it has become non-linear inherently. Now we want to approximate the system around its equilibrium point. The point is to find the equilibrium point first. What is this called? X1, x2. What is actually this x's?
The states.
It's a state. Okay. S1 and x2 are two states. What is x1 dot, x2 dot?
The change in the state.
Exactly, very good. It's a change in the state. X1 dot, x2 dot will be dx1 dot. If I say x1 dot equal to dx1 by dt. So over a period of time, dx1 cap minus x1 divided by dt. So how the x1 changes from one period of one time frame to another time frame. This has been saved in this x1 dot. So x1 dot can also be termed as state trajectory of the x1, right? So this information, the change of the state from one point to another point or one time of reference to another time of reference, we call it as x1 dot. That will be stored in x1 dot. So when I say if I put a p here and it goes to this, first time frame it is here, second time frame it is going here, third it is coming here, fourth, fifth, sixth, seventh, at eighth it is reaching its lowest point possible. Then it is not moving. So how my x1 trajectory will be? At first point, if this is 0, at first point x1 dot I'm drawing. x1 will be here. At second point it goes something here. Then here, then here. Then it keeps reducing. And this point, for the 8th point, x1 dot will be here. If I do the 9th, will it change?
No.
Because it reaches the stability, because it reaches its equilibrium, so there will not be any change in 8th to 9th. So after 9th it is not going to change until I give any force. So we are going to study this. How we will study this? We will equate this x dot equal to 0. So whenever there is no change in x1 dot that is equal to 0, then you are saying the system is in the equilibrium point. So now what I'm going to do, I'm going to equate this x1 dot equal to 0, x2 dot equal to 0 to find the equilibrium point. You sure why we are doing this?
Yes, ma'am.
Now if I just equate this equation, x2 equal to 0 minus x2 minus sine x1 equal to 0. Now what I'm getting, x2 is always 0, x2 will be 0 from the first equation, second equation. In
One
second,
doubt.
yeah.
So this looks very similar to our transient and steady state.
Yeah, we can relate to that easily. Yeah. In time domain, these are different representation of the same system, right? More or less the concepts are relatable, but it's in a different representation format. Whoever is comfortable with different kind of representation, they can go with that particular represent. That's it. Everything is going to point out to the same system unless it is linear system. Now we are seeing what non-linearity will come and how we can approximate that kind of stories we are moving. But the tools are same.
Oh, okay.
Right. From the first equation, I am equating to x2 equal to 0, x2 dot equal to 0. So from the first equation, it's always x2 equal to 0. I am substituting x2 0 here minus sine x1 equal to 0. So minus sine x1 equal to 0, then sine x1 equal to 0. Minus is minus, it will go. Now for what values of x1, this term, entire term sine x1 will be 0.
0, 180, etc.
Super. But some of us will make mistake, like only 0 they will consider. They won't consider sign of pi. They forgot about it. But you have to find all the possibilities that is giving 0 for this expression. So the equation would be x1 should be x1 equal to 0 comma pi comma 2 pi comma up to n pi. So I can write it in terms of 0 comma n pi, right? Where n goes from 0 to 0, 1 up to natural number n. So this is my equilibrium point. X2 is always 0. There is no further change in x2. Only 0 is its equilibrium point. So if I draw a trajectory for this, x1 for x1, for all values of pi, wait. From 0, for all values of pi, for example, this is scale to pi, 1 pi, 2 pi, 3 pi, some for 1 pi, 2 pi, 3 pi, it is into pi, okay, not just 1, 2, 3. This will be linearly equilibrium. For this is for x1. For x2, only this is the equilibrium point. No other point is its equilibrium point. So for a linear system, this is very important concept. Please keep this in mind properly. For a linear system, an equilibrium point will be unique, either unique or it is a continuum of equilibria. It will be we call it as continuum of equilibria. It's like a plane in a 3D space. So there will not be any discontinuity. Either it has only one single equilibrium point, otherwise a continuum of equilibrium point. You cannot find 2, 3 equilibrium point at the same time for a linear system. But for non-linear system, there can be unique equilibrium point, continuum of equilibria, and also a separate or 2, 3 equilibrium point. Okay. Now, first we found the equilibrium point. The point, this is in between concept we learned, but this is not into the steps. Okay. The first step we found the equilibrium point. The second step is find to linearize the system. What is the system? X1 dot equal to minus x2 plus x2. X2 dot equal to minus x2 minus sine x1. This is the original system. We found the equilibrium point as x1 equal to 0, x2 equal to 0 comma n pi. Now we are going to linearize the system. You all know the Jacobian, right? Jacobian matrix, right? Jacobian matrix J will be dou x1 by dou x1, right? Dou x2 by dou x1 up to dou xn by dou x1. Similarly, dou x2 by x1 by dou x2, dou x2 by dou x2 until dou xn by dou x2. Similarly, it will come until dou x1 by dou xn, dou x2 by dou xn until dou xn by dou xn. Why do we use dou instead of d? Because variables are more than one, multiple variables, right? So we are using partial differential equation instead of differential equations. So this is your Jacobian matrix. We are going to find Jacobian matrix for your original state space representation. So our system x1 equal to x2 dot equal to minus x2 minus sin x1 can also be written in terms of matrix, right? x1 dot x2 dot equal to 0 1. How do we write this? It will be minus 1 minus sine, but you won't write minus sine as it is like this. Okay, that's why we cannot write it in terms of linear system. That's why we are writing. But you can write it like this, right? 0 x2 minus sine x1 minus x2, right? So
Yes, ma'am. We can write like this.
this row will be x1. This row will be belongs to x2. Right.
Yes,
Now,
ma'am.
if I want to find the Jacobian for this will be dou x1 by dou x1, dou x1 by dou, sorry, 2 by dou x1, dou x1 by dou x2, dou x2 by dou x2, since we have only two states. So first of all, first row, we are going to differentiate in terms of x1. Are there anything in first row? Nothing, right? So the first row will be 0. This will be dou x2 by dou x1 also be 0. This is 1. So the second row, if I differentiate sin x1 by sin x1 by, no, I'm making mistake somewhere. It's not supposed to be like this, right?
Yes, ma'am. This is not Jacobian, I guess.
Though if x1 is not there, so x1 0, x2 is there. Oh, yeah, the mistake is here. It's not x2, it's until xn. Okay, that's what I made mistake. Here it will be x1, x2. This is the top will be constant. X2 dou xn. So this will be, right. It will be dou x1. Dou x1. The numerator will be constant for all the columns. So this will be dou x2. Everything will be numerator will be same until I reaches I have written in the different way. Like instead of rows, I wrote it in columns. Xn by dou x1, dou xn by dou x2 until you reaches dou xn by dou xn, right? Now this is correct. This is numerator, not denominator. This will become x1. Numerator will be same, denominator varies. Okay, that. Now if I write, first what I want to do, looking for the first equation. First equation belongs to x1, second equation belongs to x2. So dou x1 by dou x1. In the first equation, are there any, okay, dou by dou x1 of x2, dou by dou x2 of x2. This will be easy to see, right? Dou by dou x2 of minus x2 minus sin x1, dou by dou x2 of minus x2 minus sin x1. Now you say dou by dou x1 of x2 will be x1 variable is not
Dou
there,
of
right?
X. Yes, ma'am. X1 is not there.
So it will be 0.
Okay,
Differentiating with
ma'am.
respect to different variable, since there is no variable according to the denominator, it is 0. Now differentiating with respect to the same variable, it is like d by dx of x. What it is?
1.
1.
1.
So this will be 1. In this term, any x1 variable is there? It's there, right? Dou by dou x1
Yes,
of
ma'am.
x1 is there. So this will be dou by dou x of 0 minus sin x1. So
Sine
it
of
is
x1,
will be
so it will come
minus of
minus of cos
cos x1.
x1. Hmm.
Sin d by dx of sin equal to cos d by dx of cos equal to minus sin. So minus is always already there, so it is minus cos. Now this variable will go to 0. Minus x2, it is minus 1. Dou by dou x2 or minus x2 is equal to 1. Now we are going to substitute x1 equal to 0, x2 equal to 0, comma n pi. Linearizing, this is what called as linearizing around equilibrium point. Now we are going to substitute wherever this is x1. Wherever x1 is there, we are going to substitute 0. 0, 1, cos 0, cos 0, 1 or minus 1?
1.
Cos 0, 1.
Ma'am, 1.
Okay. Minus 1 as it is. So this will be 0, 1, minus 1, minus 1. So this is your linearized form of your nonlinear system. Now we have converted. Now we have converted x1 dot equal to x2, x2 dot equal to minus x2 minus sin x1 to A matrix, that is a linear system. Now we can find the stability. How do you find the stability? Eigenvalue of A. So quickly I will do and see whether the system is stable around this point. This will be lambda minus 1 minus plus 1, lambda plus 1, lambda square plus lambda plus 1 equal to 0. Okay, it will be s minus 1 minus 1. It will be stable system. The point you don't have to forget is we have two equilibrium points here. Since we don't have variable of x2 here, we are leaving it. But if somewhere has, for example, cos x2, if it is there, then you have to substitute both 0 there once and you have to find one matrix. That is the linearized version of the equilibrium point 0. Then you have to substitute n pi on that matrix. Then you have to find another A matrix, that is a linearized form of the nonlinear system at the equilibrium point n pi. So this is the very important point while doing this linearization. So in your example, exams or in assignments, we will give equations or any systems with multiple equilibrium points. So you have to find the linearized Jacobian form for all the equilibrium points combinations. 0, 0 and 0 comma n pi. You have to find two combinations you have to find here. Clear? For some systems, you have two equilibrium points. For example, 0 comma n pi for first state and 0 comma n pi for second state. Then you have to find 0, 0, 0 n pi 0, n pi n pi. That you have to find. Four linearized form of equilibrium points you have to find. Okay, we will conclude it here. I'll be here for 5 minutes. You can stay back if you have any doubt in the particular session today.
No, ma'am.
Okay, then. Next week, professor will come for the live session. So please do attend the session. Sir will teach you some concepts.
Ma'am,
Wednesday.
next week or next class?
Sorry, next class, Wednesday.
Wednesday. Today is Monday. Okay.
Same week 10, ma'am.
What?
He'll teach week 10.
Yeah, week 10.
Yes, ma'am.
Some of the concepts in week 11 also. Some controller design sir might take. I'm not sure. Sir will take some class
Okay.
on
Yeah,
stage.
we will join.
Okay, thank you.
Ma'am, just inform this thing in G space by your side. Then also it would be good.
Okay, but I want them to join by themselves. Nobody is attending the live session most of the time. So if they listen
Uh,
to this video, let them join.
okay. Actually, it's also like that today in our one of the course DSP, our professor has joined today
Oh, okay,
by
okay.
uh, by encouraging by our instructor only. So therefore, I
Okay,
also asked to write in G space.
okay, let me put it there. No problem.
It would be good. Means
Yeah, okay. Right. Otherwise, they will also get live session of that. I will
yes,
put it
ma'am.
in the. Okay. If you don't have any doubt, we'll wind up the session. Thank you.
Yes, ma'am. Thank you, ma'am.
Thank you.